look at Huffman coding algorithm first, and then we can go to the quiz. And after the quiz, we will do the, or maybe towards the end we can do the quiz. We will do the lab first, and then after that, let's see where you guys are standing. We will do the quiz um, for the um, for the unit 3. Huffman coding an algorithm is a lossless data compression algorithm. In lossless compression, the original data can be perfectly reconstructed from the compressed data. This algorithm was developed by blah 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 in MIT. Algorithm is widely used in a mainstream compression format such as JPEG, PNG, MP3, gzip, and etc. So we always think that uh, there is no use of these algorithms. These algorithms are being used widely with these picture formats and these video and WinZip format. So let's say if you remember, if you use WinZip or WinRAR, which I use sometimes. So let's say if I have this folder or this file, let's say I want to compress, I'll go here and go to add to the archive. And archive meaning compress all the fold files and put them in that. Uh, so I don't know how much is the size of this file. Let's see how much is it. Properties. It's around 2.87 KB. Okay, the original size of it. Let's say if I want to compress it, and I want to compress it, I think there is a in a zip format. Let's say in RAR format, it gives me a little bit more because it's RAR software. I'm thinking about the save the file with security. I think there was, yeah, here it is, compression and set passwords. Compression. As much as we want to compress the data, we can do that. Text auto compression is disabled, but if I'll do enable that, that will be more brute and more aggressive in the comparison. So these are the comparison that it is talking about. If you look at this gzip or gunzip file, which is Linux compression way of compression, but there's no limit to it in WinZip and uh, WinRAR. So I can do that. Compression algorithm can be applied. I can split into multiple files. If I want to exclude some of the files not to be compressed, I can do that. But I'm not going too much into detail of how the compression works. And we can set up the password and the security to it. But let's say if the original file size was this, so now I compressed it. Let's put them side by side. How much is this one? 4 KB and 2.87 KB. So it should be it will be a little less than what it is here. 1.47, even though size on the disk is still negligible and didn't reduce, but as you can see, the size of the zip file versus the size of the actual file is compressed. Whenever you will compress the video file using the WinZip, it will not affect too much. Keep that in mind. Pictures can be compressed. Uh, Excel files, Word documents, they greatly get compressed, but not too much about, not too optimistic about videos cannot get compressed too much unless you are using a technique of uploading it to YouTube and then downloading it. Then it will reduce the size, or you do some kind of a exclusive video compression software that without losing or compromising the quality of the video. But coming back to these algorithms are used in compression of JPEG, PNG, MP3, and all these different files and etc. But what is the algorithm? So let's say if I want to have this uh, this text to be compressed, or not compressed actually, create a lossless data compression algorithm so that we don't lose the data, we still have the data available, and then we are able to compress it. So the sentence that I am looking to compress is, hi there, where are we? Actually, this is the sentence. So if you look at it really closely, we have cut it out a little bit, but as you can see it, hi there, where are we? This is the actual uh, text that is written here. In this actual text, we have what we are going to do now is, and this is not the Huffman algorithm at the moment I am discussing. I am just discussing what will be the benefit of using the Huffman algorithm, and you will see 2 or 3 slides showing you the benefits which you will learn in a moment. This algorithm that I'm using, I'm not using Huffman algorithm. As you can see, the top of the slide, it does not say Huffman algorithm. This is about Huffman algorithm, and this is used fixed length encoding. So we are using fixed length encoding here, but we will also be using the Huffman algorithm. So let's do it in a very quick way. So what we do is we take out the each alphabet or a symbol and put it under the symbol column. Then what we do is write their frequency. So A is repeated only once, E is repeated six times. So E, capital E, capital E, capital E, capital E, and capital E 6 times. So we have gone on and write down the frequency of each character, including space. So 1, 2, 3, and 4. 4 times the space is used. I'm coming to the encoding part here. Let's say if I want to write the encoding, very easy to write. Start from 000 with the binary digit encoding 001, 010, which is binary number again. So out of all these, we are able to at least have 8. We have 8 symbols, so we are able to generate 8-bit data. So starting from 000, we end up at 111. Very easiest way to create binary table is like this: 0 1 0 1 0 1 0 1. The next one will be 0 0 1 1 0 0 1 1, and the last one will be after 4: 0 0 0 0 and 1 1 1 1. And this is how you create, very easily you can create binary numbers for all of these. This is not relevant, and keep in mind this is the frequency and this is not the conversion of this. This frequency conversion is not the encoding. We are just associating the binary number to each symbol. Frequency still stays the same. 16313 124 is the frequency. Now once we have that, we have 8 symbols. Yeah, and we keep writing. The total number of frequency is 21. The total number of frequency is 21. Now if I need to write this down here, hi there, how are we? This is the actual sentence that we worked on, and we converted this into this format with along with the frequency. So if I ask you to write hi, you start with H. H is 010. You type 010. Then I is converted into 011. So if I'll type 011, at the end I will have, I'm not going through this whole, but dot dot dot, I will have the whole sentence being encoded using the fixed length encoding algorithm, not Huffman coding. Using the fixed length encoding algorithm, I have this whole sentence. Hi there, how are we? Whatever the sentence is, we will be able to encode it this way. So if I want to look at the size of the compressed string, that can be easily be found. Each encoding is 3 bits: 000, 010. How many numbers we have? 3. I will have sometime I will have actually if I'll use this, but anyways, it's not drawing it here. Okay, this is not the right. Okay, I will use the other tool or something. So three bits. Each of them is a 3-bit. So total number of strings I have, or total number of frequency is I have is 21. Then I will multiply it by 3 because each letter is a 3-bit. So I will end up at 21 multiplied by 3 is equals to 63 bits that I will be using the fixed length encoding algorithm. I'm able to actually convert this whole sentence into bits. That's one achievement. The other achievement is size of the compressed string is 63 bits. So let's do this with the Huffman coding algorithm. We already have ignore this, drop this column now and continue from where we left. We have a symbol and the frequency table. At the moment we have a symbol and frequency table. If we just consider that A is 1, E is 6, H is 3, it is not a sorted list. So first thing the Huffman coding algorithm says is sort the numbers, sort the given symbols, which are the alphabets, according to their frequency. Mostly the alphabets, one is the space, so we are calling it a symbol, but we are sorting it based on the symbol and their frequency from lowest to highest. So if you are writing algorithm in Java or Python, what you will be doing, you will be going through, you will take the input from the user, or you will take this input, hi there, where are we, as a string that we are after to compress. What I will like to do is to write this algorithm for me as a start part, that you will take an input from the user and write the frequency of each symbol in there. That will be the first part of the algorithm. I will not stop here. The next part is in the step number 2, what we will be doing. From the frequency table, select the two symbols S1 and S2 with the least frequency, say F1 and F2. In this case, we have A and I are the ones that have the least frequencies. They are only repeated once. So what I'm going to do is I select A and I and put them here and create nodes. So I know that A has the frequency 1, I has the frequency 1. Let's create, these are the two nodes that I created. Let's join them together. Combine S1 and S2, which is the third part step of the Huffman, is that combine S1 and S2 to create a node symbol S12 with the frequency by summing up the frequency of the two individual nodes A1 and I1. So if I combine A and I together, they are frequency together to be 1 and 1. 1 plus 1 is 2, so you put them here. So this becomes one node, A and I. Let's move on to the next one. Yeah, this is basically what I'm saying. Remove the node. Okay, remove the node S1 and S2 and insert S12 with the frequency and keeping it sorted. So because I have A and I here and I combined A and I here, I will not need A and I in the table. Instead, what I did is I joined them together and put 2 in front of them as a frequency. Okay, so A and I individual nodes are gone. The combined symbol is showing up here now. So the symbol table is shrinked a little bit based on A and I are gone. So algorithm is working on the side, visualization is working on the side, and the working of this algorithm is also here. So you have to keep three things in mind rolling through together at the same time. Now what is the next target? Pick the next two with the lowest frequency. Here I will start with T and W. So I will say individually broken. T and W will be put in a separate node. So we left this part alone and we started all together one with this one. With with T as 1 and W as 2, they are combined together, right? And they are written as TW3. So this will be removed in the next step, which we will see in there. According to this part of the algorithm, remove S1 and S2 and insert S1, 2 to the frequency table while keeping it sorted. So that's what I did. I get rid of T and W, and in T and W is now been denoted as T and W, and A and I is already there. Now here's the issue. Before I go to H and R, which one has the lowest frequency? These two have the lowest frequency, or this is actually equivalent here, but isn't it better that I can join the already glued together symbols together? We can do that as well. So if I join AI and T and W together, what I need to do? Add the two frequencies 2 and 3 together and make it a 5. But the next step would be that AI and T and W will be removed and will be changed into 1 together. AI, T and W with the frequency 5. In the next step, going fast forward, HR is joined together and HR is here, right? So HR is here, H and R individual nodes are taken away, and we have this one bubble again popping up. So H and R is joined. So H and R, next would be space and A and I and T and W. So space is put on the left side, and one thing that I am noticing is the left will have the lowest and the right will have a highest. But keeping in mind I can join space and AI and T and W together, this will be removed in the next slide, and their frequency is 9, combined frequency is 9, so I can put the combined frequency here and I put that as a symbol here. So space along with AI and T and W are joined together and they are put in here in the table here. We are doing as granular as we can. E and HR will be joined. So is there any E so far? No, E is added here and HR is here. They will be joined together, and then we have HR and E with the frequency 12. At the end of the day, we will be joining all these together in one big tree. So now we have left with these two, and we are continue to do forward, and we have the last node or the very first node of the tree will have space and AITW with the 9 frequency and HRE with the frequency of 12. When they will join together, the frequency is 21. So at the end, we have this structure prevalent now that has came out on the screen diagrammatically here with the frequency of 12. Next part, assign 0 to every left branch and assign value of 1 to every right branch. So left branches will have started to be 0. This is the left branch. This is the right branch. So right, as soon as you turn right, you always say 1, 1, 1. As soon as you move left, you always put 0. Doesn't really matter if from starting of the tree towards the end of the tree, you will have this. So now we are coming up with a point here. Let's say if I want to traverse to A, what will be that? 0, 1, 0 and 0. So there is a code that is being generated for the letter A. If I want to traverse T, I will have to go 0, 1, 1, 0. So this has created us one scenario that every single letter will have a different letter encoding. So it's not that letter encoding that we looked at the start of the lecture. It is a different encoding because we are going through the Huffman coding algorithm. Let's put that down in a table. So if I need to go to the space, 0, 0 is the easiest way to reach that. So I have given you traverse through the node. If you want to go through traverse through the node, you are good. You can traverse through the node, no problem. Space is 0, 0. A is 0, 1, 0, 0. These are a couple of examples. Now let's put them together in a table. It doesn't really matter how you want to put it, but look at this. Start with the best way is to start with the left and go towards the right. 0, 0 is put here for the space. If you want to traverse A, 0, 1, 0, 0, A is traversed. I, you already know. T, you can know. W, you can traverse. And all of them you are traversing. Now we have a new encoding generated now on the screen. Symbol and then encoding. Where is the frequency? We will look into the frequency in a moment. There will be a different frequency here. So symbol, you are left now. The important point is you are left now with the symbol and encoding. But where is the frequency? We are coming to that now. Symbols which are more common are encoded using the fewer bits than less common symbols. So the less common symbols have higher encoding. So let's say the ones that have, and that's a proof here, the number of time E is repeated, it is encoded with a very less number of uh, encoding numbers, with a very less number of encoding bits, I would say. So space is the second one. It is also left with 0, 0. A, which is only repeated once, has the 4-bit encoding scheme. Okay, so these, let's put the frequencies together, which we already know. Frequency of space is 4. Frequency of A is only 1. I is only 1. T is 1. W is twice. And then so encoding we already achieved with this chart. Now we are putting together the frequencies. Now here we look at the symbols which are most common are encoded with fewer bits than the less common symbol. This ensures that the total number of bits are minimized. So the total number of bits are minimized. Total number of bits that we are going to save in this case, which is not too much, but we will be able to save more in a longer text if we are compressing that, and that's what essentially happens in all those algorithms which we discussed in the start of the lecture. So let's look at that. How many times 0? How much is the length of this encoding? 2. 0, 0. Length of this encoding is 2. So what you will do? 2 multiplied by 4. What is the frequency? 2 multiplied by 4 is 8. What is the frequency? What is the encoding length here? 1, 2, 3, and 4. 4 multiplied by 1. You put that here. Same with I. How much is that? 1, 2, 3, and 4. 4 multiplied by 1. 4 multiplied. And remember, this 4 multiplied by 1 is different than this 4 multiplied by 1. This is the frequency. Sorry, this is the frequency, and this is the total. This is the number of space. But from there onwards, for the next three cases, one with the case with I, T, and W, they are all multiplied by 1. 4 multiplied by 1, 4 multiplied by 1, and 4 multiplied by 1. And you go on and do that until you hit 2 multiplied by 6, which is for the E. At the end, what we are having is the less than total number of bits than we used in the fixed length encoding algorithm. So Huffman encoding algorithm reduced 5 bits for us. Not a lot for this small sentence, but if we have a bigger sentence, or if we are able to convert a bigger text and able to apply these two algorithms, we will definitely find Huffman as the better winner. Again, I will say in another format where you are encoding a picture, how you can encode the picture. If you are encoding the picture, at that time what you will be doing is you will have, let's say, 256 color RGB. You will assign each color a code, and you are trying to compress that or a symbol to each color, and then you are trying to compress that. So you need to assign every different color a symbol, and then create the encoding for that how many times this picture has used that color in that, and then you encode that, and that's how the encoding happens. This is Huffman coding that we are looking at, so we are not going into those picture related encodings, but here we are able to justify that we have saved 5 bits. Not a lot, again, in the context of what we are doing. When we looked at the previous slide where I was looking at fixed line coding, we have used 63 bits compared to what we have 58 bits in this scheme that we have used. So the Huffman coding encoding algorithm is discussed in the class pictorially, theoretically, and algorithmically. Uh, this is actually creating a tree structure, which is the main part where you kept the encoding going on. So if I'll give you any other sentence and I ask you to encode that, and if depending upon if I'll give you a 2-line sentence, then you will see a lot of bit differences will be appearing. This is a small sentence, not even a 1 line. It's a half a line sentence. We already saved 5 bits on it. So we can use this algorithm for that. So that is my take on Huffman encoding algorithm. Huffman